Hi, everybody. So now I want to take our multivariate results and get a geometric perspective on those. And we'll see that it's a very similar picture in higher dimensions to the picture that we saw in 2 dimensions, namely that you can think of the solution to the least squares problem as finding the closest point in a certain subspace of a vector space to a given vector. And so let's look at that a little bit more closely. And to make progress on this, we have to, let me just remind you of the formulas that we showed last time. We showed that the minimum value for the error term, which was y minus xm squared, occurred when the gradient of the error was 0, and that happens when x transpose y minus x transpose xm equals 0, and in other words, where x transpose times y minus xm equals 0. And let me just remind you here maybe one more time that x and y here are constant matrices that come from the data. And m is the variables. It's got k plus 1 entries. And x and y, so x is just maybe to keep hammering this home, it's n by k plus 1, and it's the data matrix, and y is the target. It's the observed variable. So how do we make sense out from a geometric perspective of this equation? And for that, we need to remind ourselves a little bit about linear algebra. So let's remember that if you have a matrix like x is a given matrix, which is n by k plus 1, the column space of x is the subspace of Rn spanned by the columns of x. So each column of x has n entries. There are k plus 1 of them. So the column space is spanned by k plus 1 vectors in our situation if we're using our matrix x. Now, it may have dimension k plus 1 or smaller because the columns of a matrix need not be linearly independent, but let's not worry about that for the moment. Now, let's suppose that we take a vector m, which is m1 down to mk plus 1. Think of it as a vector with varying entries. When we multiply x times m, we get an n by 1 vector. So as m varies, xm gives elements of Rn. But in fact, each of those elements belongs to the column space of x, because if we write our matrix x, and here's m1 down to mk plus 1, when we do this matrix multiplication, the first entry of the product, here we have x11, x21, x12, The first entry here is going to be m1 x11 plus m2 x12 plus mk plus 1 x1 k plus 1. And this is just the rules for matrix multiplication. The last entry is going to be x n1 m1 plus x nk plus 1 mk plus 1. Whoops. And that's just m1 times the first column of x plus m2 times the second column of x plus mk plus 1 times the last column of x, using the Python-inspired notation where this means let the first index run all you want, but fix the second index to 1. So these are the columns of x. In other words, xm varies over the column space of x as m varies. And so if we look at y minus xm, here we have, I'm going to draw the picture like this. Here we have the column space of x. Here we have y. Y doesn't lie in the column space of x, because if it did, it would mean that y was exactly equal to some linear combination of the columns of x, and then our problem in least squares would have an exact solution, but we're assuming that's not the case. And as we look at the norm of y minus, let me do it this way. If we look at y minus xm, so here's xm, it's a general point in the column space of x, and y minus xm is the vector that connects y to xm. So when we minimize what we're doing, when we minimize y minus xm squared, what we're doing is we're allowing xm to vary over the column space of x. And we're looking for the point in that column space which is closest to y. So our solution to the least squares problem is, what is the point in column space x closest to y? And we have a formula for what that is. It's given, we know that m has to satisfy this condition that we started out with, that x transpose y minus xm equals 0. So this happens for xm when x transpose times y minus xm equals 0. Now, how do we interpret this condition? Well, remember, as m varies, y minus xm is the vector. If I try to draw this picture one more time, here's the column space of x. Here's y. And I'm considering a moving point in the column space, and I'm looking at the vector that joins a moving point in the column space to y. And what is this? That's my y minus xm as m varies. And what does it mean to take x transpose times that? Well, x transpose is a matrix whose rows are the columns of the original x. And when you do this matrix multiplication, what happens? So this is now a k plus 1 by n matrix. And what you're doing is you're taking the, here you have y minus xm. That's the column vector which corresponds to this distance. And here you're taking a row of x transpose, which is a column of the original x, written on its side. And when you multiply it, you get a vector whose entries are these products. So in other words, what you're doing is you're taking the dot products, so the entries of x transpose y minus xm are the dot products of the columns of m, columns of x, with y minus xm as m varies. What does it mean to say that all of the dot products are 0? It means, so if all the dot products that means that y minus xm is perpendicular to a spanning set for the column space of x, which means that it's perpendicular to any element of x of the column space. In other words, the m that gives us the best solution is precisely the point where the line from y to the point in the column space of x is orthogonal to the column space of x. So if you think of the column space of x as like a hyperplane in a high dimensional space, and you think of y as a point sitting outside of it, then the m, the solution to the least squares problem, you change m until xm is a point so that the line from y to xm is perpendicular to the plane. This is exactly the situation that we saw in the two-dimensional case. And so the predicted values are exactly the points that if you take orthogonal projection, I mean, maybe I could draw, let's look at a side view. So here's the side view. This is the column space of x. It may be high dimensional, but we're looking on it from the side. Here's y. The closest point here, which is the predicted values of y, is the point where the line from the predicted value to the measured value is perpendicular to the column space of x. That's what the condition y minus xm squared minimized, or in other words, x transpose y minus xm equals 0. That's what these conditions mean.